Good day, good afternoon, all. This is Anirban. Today, I'm coming out with a new practical tutorial to show a RAG pipeline with multiple LLMs. And basically, as you can see, you can see me in the video also in the corner. And this is basically, in between, I was doing some videos where my image was not there, and I remember one of my classmates from college, whom I passed out 30 years back and last met him about 5 years back. He was looking at one of my videos, and he could not see me. And when he met me, he was on the way to meet me. He was very disappointed, and he said, "Nirban, I looked at your video, but there's nowhere you can be seen. I'm only seeing a black screen." To add to it, he was seeing on a mobile screen, and he could not even read the code. He said, "I see some black screen, and you talking something," and it was really, I am really disappointed. So I thought of adding my image. And also, one of my friends recently started his video series, and I saw he is explaining very nicely the basic concepts of AI as part of his tutorial series. So maybe it helps to have a my image at the corner, some human interface to it. So basically, what I'm trying to show today is my learning from some of our recent implementations with RAG pipelines, retrieval augmented generation pipelines, using open source LLMs as well as the traditional paid LLMs available as API services, be it the OpenAI, be it the Gemini Pro, and do a comparison by running the RAG pipeline on some simple data which I've downloaded from the internet. So basically, the concept of retrieval augmented generation, as we all know, is these LLMs are not trained on any specific proprietary data. So, for example, if a retailer is trying to implement this, the knowledge base that exists within that retailer is not going to be available in any LLM. Or a car manufacturer, if he is implementing this, the the information, the database that it has is not available to any LLM to train on. Or, for example, a pharmacy company is implementing it. So when this application is built, the LLMs need access to the proprietary database of these settings of these domains to answer the query appropriately. So that is what we are trying to simulate here. And when we talk of a retrieval augmented generation, one of the major ingredients is a vector database. A vector database which stores the embeddings of chunks of text from these documents in a vector database, and basically can give the similar documents based on a query. Right? Now, that is in one word. But when it comes to vector database, there are many considerations based on which a vector database can be chosen. For example, do I want my vector database to be stored on the cloud, or do I want a native vector database, right, which is stored on my system, on-prem system, and my data, I'm not sure I want my data to leave my boundary anytime, even if it's in a vectorized format. We have seen many customers say that. Do I want the vector database to support hybrid search, which means multimodal search? It stores images as well as documents, and I can search based on my query on the images as well as the documents. Multimodal search or a hybrid search, right? Do I want my vector database to, for example, to search over millions of documents? I mean, it's one thing if I have one or two PDFs. It is another thing if I have 50,000 PDFs to search through and come out with a response in few seconds, right? If response time is a criteria, which it mostly it will be if it's an online system, right? So how do I search millions of documents and come out with a very quick response time? So all these considerations, and one of the questions we have heard in many cases, how do I select a vector database, right? So one of the nice articles that I came across, it was referred by in one of the training courses that I have done from a very prominent institute, is this article, which I am referring to here, the dataquery.com. I mean, I could have gone directly into my code and explained it, but it's better to have some background on how to select these things. What are the architectural decisions, so that we don't get stuck up at a later point of time, right? So hybrid or keyword search, on-premise or cloud native, open source or fully managed, right? All these, some of these are some of the decision factors. Choice of programming language, timeline, right? How these vector databases got built, right? And so all these things, we can. I'm just referring this article over here, and today I'll be using the FAISS index from Meta AI, which is known to be one of the best databases which supports millisecond level retrieval from many millions of documents. It has been benchmarked over billions of documents. So you can just give Meta AI FAISS, and the first page will hit is basically the FAISS page, and we can read this what it means, right? It provides scalable similarity search functions. That's the main important thing about it. It's implemented in C++ with a Python interface and GPU support. So you have the FAISS GPU Python library which has to be installed. So it gives step by step how to use FAISS, what are the search algorithms, how to do various types of searches on millions or billions of documents. So what are the such algorithms it supports and all these things. So it says here it includes nearest neighbor search implementation for million to billion scale data sets that optimize the memory speed accuracy trade-off, right? FAISS aims to offer state-of-the-art performance for all operating points. Here we are using the LangChain supported FAISS. LangChain in its vector stores, LangChain community vector stores, FAISS is now supported. I mean, it is supported for a long time. Now it's under LangChain community, and that's what we are going to use. And we can see this reference here in the. I'll give these URLs in my GitHub, so we can see all these similarity search and everything over here, right? So all these methods. So in order to go towards open source, the embeddings that have to be generated from the text, I'm going to use Hugging Face embeddings, which is basically using Hugging Face, and I'm going to ingest the documents using Hugging Face embeddings. So normally what I do is I create a batch program to test my vector database operation. So here is my batch program called search test.py, and if I run this, I can see the documents which is ingested in my vector database using this list database functions. I have two documents, and so these two documents, the important thing is when I'm chunking and adding these documents, I'm also adding the documents metadata. So if you are going through the iterating through the documents in the vector store, one thing we have to understand that a document in a vector store is not a document what we understand as a document. We understand a PDF file as a document, a Word document as a document. In a vector store, the chunks are the document. So one document may have 50 chunks of text. So each of these is termed a document, right, in a vector database. So if I am to print this in while iterating to the vector store, I'll see each of these chunks and their IDs along with the document metadata. And if you see, I'm adding these document names to a set because set contains only unique elements. So finally, I'm returning that set. And if I print out that set in my main function, I can see the documents over here. So let's rerun this program list vector db. And we can see that finally it said there are two documents in the collection. This is one document, an invoice of a book I bought, and another is a climate report which I downloaded from the internet. This is to simulate two different areas, different types of topics, and see whether the querying is working on that. But if you see, when I'm iterating through the document chunks, it is printing the same document multiple times because each of these IDs is actually ID of a document as per the vector database convention, which is a chunk of text, and it make, gives the same document multiple times. There is no direct interface to list only the document, so that is the way indirectly we are, you know, getting the list of documents from a vector database like FAISS. Now, here is one point I wanted to say. In many of these videos that I make, I have got good, uh, good suggestions. I've got good feedback from IT professionals in some of the top-notch companies. They told me in message that they liked my videos and they found it useful, which is a very good thing to hear. But one thing I haven't found is, probably it's not in our culture. I haven't found anybody, saying that this can be done in a better way. What you have shown is good, but I can do this in a better way, right? So that is what I'm looking for. Somebody can show me that this can be done in a better, more concise way or a more efficient way. That will be really good. So please try to do that, and let's see where this goes. So, for example, this is one inefficiency. Now, if I have, for example, millions of documents in the vector database and I want to list this way, it's not going to be efficient at all to iterate through all the chunks and adding the names of the document from the metadata into the set, right? So I'm now removing this printout so that it goes back to the original state and I can see the number of documents in the vector database, right? I have add vector database also. Here the important point is when I'm adding a vector database, the important thing is I need to add the metadata. So how I'm adding is basically I'm creating a text splitter, which is my recursive character text splitter, which we have found from experience to be working very good with a chunk size of 1000 and a chunk overlap of 200. Work the best for us in many scenarios. And then for when I get this document, I basically iterate through the pages of this document, right? And this pages is already provided to it from PyPDF loader, right? And I create the chunks, and for each of these chunks, I append to this array of list of documents, and what I append is a document object. So this document object is basically, if we look at it, it is a LangChain schema document, right? LangChain schema document. So this document object I create, and the page content is the chunk, and the metadata is a dict object with the page number and the document file name of the document. So I can have any metadata here. I can have the section number. I can have any other thing that paragraph header, anything that I need, I can put as a metadata over here. This is important because when I'm retrieving the results, business people all most often wants to know, okay, you got this result, but from which document, which page number is this result coming from? It's an explainability aspect. So when we're adding a document to a vector store, it's always important to have this, right? So that is how it is created. So for example, if I search the vector database by invoking the search vector database function, so I'm asking a question: how much did the temperature change in 2011 compared to 1850? Uh, I'll see some vector search result, right? So this is the search result it has given me. And if you see, the metadata is page number 7 of this document, IPCCR6 SYR SPM.pdf, which is downloadable from internet. It's a climate change report. And this particular section, the chunk of text, it actually talks about the temperature change, how the temperature changed over 150 years. It gives the details of that. So it has hit that particular information and got it. Now, this is what will feed as a context to the LLMs. So, the same context, my vector search is not going to be different based on the LLMs, right? The same context, same vector search will work for multiple different LLMs, and we'll see the result, how they differ, how good is the open source result compared to the other professional LLMs. We can see that. So, starting the next part of this tutorial. So I was talking about the FAISS index and how to search in a FAISS index. So the add vector DB, which I was talking about, it loads the document with from the file name provided and provides the pages to the update document. And the update document basically stores the document chunks with the metadata. So we came to this, and when we search this, we just pass a query, and we don't have to uh, create an embedding of the query. The FAISS index dot similarity search takes care of that. We can pass a query in English, and we can specify how many top k matches to return. In this case, I've specified one, so it will return the topmost similar match, and we can see the result here, right? Important thing here is we need to provide an embedding when we are loading the vector database or when we are creating the vector database. These embeddings here, I am using the sentence transformers all impinate base v2, which is a totally open source. I need to don't need to pay anybody. I need to don't need to go anywhere, right? So this is embeddings created from Hugging Face embeddings with the model name this, and the model K works. I've given as CUDA because I'm using the CUDA support for FAISS search as well as for my LLMs. So here we can see I was using OpenAI embeddings, text embedding ADA 002, which is referred in the LangChain documentation, but we are free to use open source embeddings as well. If we want to make our solution perfectly open source, we can use that as well. So that is also working pretty good, and this is again based on our experience at few customer sites, right? Okay, so having tested our vector search operation in a batch mode, uh, we can basically remove the unused imports. Not a good practice to have lots of unused imports. Remove this. Okay. So this is my main method of my REST API framework using Fast API. So it basically creates a query app, initialize the Fast API server, and I use the same embeddings as I was showing in the batch mode, Hugging Face embeddings with the sentence transformers, and basically. So here is the thing: when we're loading up the vector database, if the vector database is already available, so if I'm using it, I'm already ingested some documents. I'm not creating it from new. It'll load that from there. This path can be fed from a configuration file, right, where the vector database is stored. It can be on a cloud storage, on a Google bucket or Azure blob, or it can be on my native system. That's the advantage of this type of implementation with the FAISS. It can be stored in a local mode on-prem or in the cloud, right? And if this is not available, it will ingest and it will create the vector database from an initial file which we can provide here. So I provided a file name here, and in case you are doing it, you will not have this folder FAISS index pg. So in that case, it will ingest and create the vector database, right? So if you look at it, what it does, the same thing that I explained, it loads the PDF file and then basically gets the pages out of it, and using the recursive character text splitter, it iterates through the pages, creates a list of documents from the chunks, and basically then we use this construct from documents, list of documents, and the embeddings. So this embeddings is very important because this is what is going to use to create the vector embeddings of these chunks, right? And same concept when you do update doc. Now the vector database is already there, and we are adding some documents to it. So all we do is instead of from documents, we say we pass the FAISS reference and say add documents. And here we pass a list of documents because it already knows what embedding it was created with. We don't need to pass the embedding model again. But the basic concept is the same. Here we are adding a document. So this is part of my ingest util. Add vector db, list vector db, right? These are being referred to from my main endpoint in Fast API. So the main method I have is a query, which is what I was referring to, which is basically querying the LLMs with the context from the vector search, right? So query method, if you see that it uses this data model, the pydantic data model, where the model name is a enum, right? It has four different model types: OpenAI, Neural, OpenHAMS, Mistral 7B, Gemini Pro, and Palm API Text Bison. And the response, right? What is the response to the query? It can be multiple responses, so it's a list. The response time, I want to compare the response times also, right? And maybe if I want to do some evaluation, some scores and all those things. So that is my setup. And if you see here, in the main, in the query API, what I'm doing is simply based on the query passed to it, which is the query field which the user is typing. I'm searching the query using the search vector diff function by passing the reference to the FAISS index, the top k reg, how many results I want, and the query itself using the same mode which I showed in the batch program. And I'm getting now the answers to the query from the LLM. So this is the generate answer method where I'm getting the query response, which is the response text and the response time from this. It is there in the QA tool.generate answer where I'm passing the model name. So depending on the model name now, it will bifurcate to multiple models. So for example, if I'm using the Mistral 7 billion model, I know that my prompt has to be formulated in this way for the Mistral model. Where do I get this? I get this in the Mistral site. So if I just search open, this is the model that I'm using, Open Harms 2.5 Mistral 7 billion. How do I know that? Basically, if I go to my code base, now this model is loaded one time at the startup of the server, right? So I am using the some of the models which I'm using. I'm initializing them at the startup of the server in the static context. So this is my model which I'm loading using the Llama CPP library. If you look at this Llama, capital L, small l, A, M, A, and the model path is provided here. So this is what I've already downloaded. Now somebody may ask, how do I download this? Is a 4-bit quantized model, mind you. I mean, any model which is open source and 7 billion parameters is going to take a whole lot of memory. The response time may be very high. We can only work with quantized models. So here we are using a 4-bit quantized model, and from our experience, we have seen that the 4-bit quantized models gives pretty good results, and it was validated by our analysts and found to be very accurate. So if we search this in the Google, the first link that we get is here, Open Harms 2.5 Mistral 7B GGUF. So if we scroll down here, we can see the prompt template that is supposed to be used for this model, which is what I'm using. And we can see the various quantized formats over here. So 4-bit quantized, right? This is the bits, 5 bits, 6 bits, 8 bits, and all those things. So here I'm using the 4-bit. Within 4-bit, again, there are multiple models, small, medium, large. So I'm using the Q40, this particular model, which you can just download it and give the path to it and initialize it, load the model using the Llama import from the Llama CPP. So if you see this Llama where it's coming from, it is coming from here. Lots of unused imports here, which I was using earlier. I'll remove this. So from Llama CPP, import Llama. Not using this, not using this. Okay. From Llama CPP, import Llama. So how do I install the Llama CPP? Basically, I've given it in the requirements.txt. We need to have CUDA enabled. So basically, we need to have an NVIDIA GPU. I am using the RTX 2060. For example, if we have the GPU running, if we give NVIDIA SMI, that is one of the good tests. We should be able to see the GPU, right? So it says that there is a GeoForce RTX 2060, and the CUDA version should be also be able to see here. That's a good proof that my GPU is up and running. But what I faced a problem is when I was installing this Llama CPP Python library, it was not utilizing the GPU. So my response time was about 2 to 3 minutes per request, which is not acceptable, right? So that's why I then Googled and I actually found this particular command very useful. This whole command, if it's used to install the Llama CPP Python, it actually allows to use the GPU. So we just give the path to our NVCC file within the CUDA distribution over here. That's all it is, and we just ask it to install the Llama CPP Python. That's all I did, and from that time onwards, I can see it is uh, using the GPU. One of the proofs of whether it's using GPU is when I start up this fast API server using this command. uvcon app dot main colon. So it's going to load the open source model using the llama cpp library to start with, and we should be able to see that. So you can see that still not done it. It's doing it now. So here we can see device. Okay, it's not finding this model. I'll have to check on this. It's- okay, but coming to this, so here we see that it's saying device 0. It has found this device 0, NVIDIA GeoForce RTX 2060. And when it says this, it is a definite proof that the llama cpp library is using the GPU. Coming to this, why is it not finding the library is something which I have to see. Open hubs. So as I was saying, it's important to load the open source model in a 4-bit quantized format using the llama cpp python library, which is what is being done here. And this model is being loaded one time at the server startup, and we can see here the llama cpp python library is used to load the 4-bit quantized model. If we search this, we can see where it's being downloaded from on the Hugging Face. Easy to see. You can search this, and the first link we go, we can see it's downloadable from here. The prompt template that is supposed to be used when using this model, and various quantized versions are available directly for download. Now, we can quantize the models at runtime using bits and byte configuration, or we can download the quantized model directly. So we even made a comparison between the 8-bit and 4-bit and all that, and we found the 4-bit quantized model working good with a good response time as well. That's what I'm trying to show in this experiment. But it's important to load the llama cpp library in a proper way so that it utilizes the gpu. And one of the important parameters while loading the model using the llama cpp python library is that we should be able to see the gpu here. And initially I was not doing that, so everything was loading fine, but my response time was 2 to 3 minutes per invocation, which is not acceptable. So one of the ways I found was to use this command, this full command, to install this llama cpp python library. Instead of just saying pip install llama cpp python, this includes the path to the CUDA NVCC, which is there in my system. And once we install it like this, I found that it's able to utilize the GPU that I have very well. So that is what it is. And we can also see how the other models are being invoked. So for example, the palm api, we pass the parameters and say text generation model dot from pre-trained text bison, whatever model is, and say model dot predict. So we need these two libraries, Google Generative AI and Google Cloud AI platform, to use these models from the palm api text bison model and the Gemini model. So the Gemini model is basically again generative model, which is coming from the generative AI PyPy package. We load the Gemini Pro model, create a prompt here, simple prompt, giving the query and the context, and say model.generate content with the prompt, and we can give the generation config like the temperature in the top P and all that. OpenAI is we have already done in many tutorials earlier. We load the QA chain from the lang chain, pass the LLM, which is the OpenAI, and give the model name, in this case GPT 3.5 Turbo, with the parameters and all that. And We just say response equal to chain dot run. Here the only difference is the input documents. It takes the documents as returned from the vector search. We don't need to provide the text. The documents as returned from the vector search is being passed directly. It's intelligent enough to extract the text from that and pass it to the query and all that. So that's the advantage here with the LangChain chain.run load QHN. So for retrieve answer with the Mistral API, we are basically using the LLM and giving the input. That's it. The input is a prompt in the particular template with the query and the context, and just saying LLM with the input. That's it. As simple as that. We don't need this construct over here. One problem here I faced is I'm not able to pass the temperature, top P, and all this. The reason being that it can be passed definitely, but the reason being this I am loading the model at startup, not to load the model at every invocation of the method. So we can take this as a configuration parameters as well and load the model at the startup with this configuration. So here is where we are passing this temperature and all these things when we are loading the model with the LLAMA, L capital small l. This is coming from this here. Uh, from llama cpp import LLAMA, right? So with that, we can test our inference with the same vector database input and multiple LLM models. So we go to our, if it's running, yeah, it's running. To a query interface, try it out, and we can say, how was the CO2 emission distributed amongst countries globally? We can ask this question. Little bit difficult question. So we ask it to OpenAI. So it's going to search and then say CO2 emission will distributed unevenly with around 35% of the global population living in countries emitting more than 9 tons CO2 equivalent per capita. 41% live in countries emitting less than 3 tons CO2 per capita. Response time is 1.71 second. We can ask the same question to Mistral 7B. See, the input is the same. The vector search is working in the same way, but we are trying multiple LLMs. That's the thing I'm trying to show. It says that from here the answer is quite good. There is some random characters here. I don't know why, but you see the answer from here is pretty good. It gives a very detailed answer, including the actual answer. Response time is 6 seconds. We ask the same question to Gemini Pro. It can't find this. This is what is surprising to me. Palm API text Python also probably the same. Doesn't have the information. It's saying the text doesn't have information. But if we refresh the question, how was the CO2 emission distributed globally according to the climate change report, we might get a better answer. So depending on the context, one of the LLMs will give better answer, and we can say here it says that this now it's giving the correct answer with the rephrased question. So depending on the situation, on the question, on the private document that we have, in this case we can read the English and we can say which is giving the better answer. But in many domain specific scenarios, we need a business analyst to evaluate this and tell us which LLM within this context is giving us the best results. And what I'm trying to show here is that normally if somebody asked me 4 months back or 6 months back, how does the open source LLMs compare with the professional API based LLMs, I would have said no, there is no comparison at all. But now we see based on my experience that the 4-bit quantized models, if it is utilizing the GPU properly, within a good response time, acceptable response time, the answers that is coming is pretty good and pretty professional, and it can rival the paid LLMs as well. And with the Pretty base coming in, there is an option to fine tune these models. Means not prompt tuning, but updating the model weights based on one's own training data, right? One's own domain specific training data. Pretty base is actually making it very easy to do that. And I've also seen Google Gemini Pro has released this feature just recently, about February March, to fine tune the model using Google Generative uh, AI Generative AI Studio. So same way we can ask this question to OpenAI, we can check the answer. So it is giving again. This is now considering the question as how is it distributed globally amongst the industries, because I didn't say how it is distributed globally, whether it's among the countries or the industries. It's ambiguous, so we have to make our question also very specific to compare the answers. But right now with this question, it is searching the vector database. That part is the same, but the four LLMs, how it's behaving, we can clearly see by changing the LLMs. We can even change these parameters as input and see whether that gives any better answer. So this is also Palm Pay Text Bison also gives very good results. So it's a quick way of checking out for your own context which one is giving better result. The FAISS index that we are using is local. There is open source, LangChain provided. It can be stored in the local on-prem server. The embeddings that we are using are not the OpenAI embeddings, but the Hugging Face open source embeddings. Models is a combination of open source and paid. And we can utilize anyone depending on our context, depending on the validation that is done by a business analyst. And it's always good to check out multiple models and see whether we can move towards open source or paid version depending on the context. There's some customers we have seen, they even told us that they operate in an environment where there is no internet at all, their devices. So their open source is the only option. So we have to, you know, here instead of five different models, four different models or four types, we might have four different open source models, right? The Mistral 7B again comes in different flavors. There are other open source models too, right? Many of them. And we can just check out the responses based on a same input, how these responses vary. We can even change the top K rag over here and ask the question to Palm API, and we can see how the response varies. We are giving it more answers from the database. Now it gets confused, right? It doesn't give the proper answer, which is also surprising. So if we give this to Gemini Pro, you can see how this works with top K rag of 3. So we are saying take 3 these things up, but it doesn't get still. But when I send this to OpenAI, OpenAI is generally giving this answer, because it's now saying, since I'm not saying countries, it is saying how is the CO2 emission distributed globally. It's saying according to the industries. So all these things, we can check out by different questions and answers, and make sure they are proper, based on the business analyst or domain experts feedback. And we can play around with multiple such models, right, from the Hugging Face repository, from be it a professional models, make a good comparison, and depending on the customer's use case, customer's requirement, we can deploy the RAG pipeline either in a local manner, on-prem manner, or with a cloud interface and all that. So that's what I was trying to show. It's a very good learning from our some of our past experiences, and just wanted to make a uh, short video on that. I hope it's good for some of the newcomers in this area. Thank you.